Okay, so let's do a straight up example here, right? Mo and Joe have clocks. They tick every 10 seconds, right? This is our proper time. Okay. Joe is flying by at 0.85c. What time does Mo see Joe's clock take to tick? And there's a trick with the speed of light, which I think we've already used. Okay. So this is just straight up time dilation. Since Joe's clock is moving, it's going to move slower. The time travels slower, so it's going to take more than 10 seconds for us to see his clock register 10 seconds. Okay, so let's just set that up. The dilated time is the proper time over the square root of 1 minus. Right, so I'm going to go 10. And then the trick with the speed of light is, of course, I can go 1 minus point. There's my velocity. Don't make it into a velocity. Nobody does. Right, and then divided by c squared. Right, the trick is that the c goes away with the bias, and you can cancel that out, and you end up just going 10 over the square root of 1 minus 0.85 squared, which is what I'm going to do here. 10 divided by the square root of 1 minus 0.85 squared. And I get 18.98. 18.98 seconds. We have only 2 sig figs, even though this one valiantly has 4 sig figs. The 0.85c gives us 2 sig figs, so we have to say 19 seconds. Yay. One thing to remember is that the Lorentz factor, that little thing there, whoo, gotta draw slower. Okay, wow, that's just messy. That Lorentz factor of 1 over, why is this so bad, minus v squared, doing the best I can with the technology I have. Okay, if you put in 0.866, roughly, just to remember, a little rule of thumb, if your velocity is 0.866c, the Lorentz factor is about 2. You double the time, you double the mass, you cut the length in half. Wow, that's almost like a chant. You double the mass, you double the time. You cut the length in half. Just remember that. At 0.866c.